This is Eric Zilke, and this is my Datum Target Optimization final report. The aviation industry creates many large aluminum structures made of spars, ribs, and longerons. These parts can be long, slender, and prone to sag when simply supported on either end. A design engineer is tasked with determining a datum scheme so these parts can be verified for geometric accuracy. These long beams must have additional datum target points called out to support them along their length. Doing this will reduce the deflection of the part under its own weight, so accurate measurements can be taken by a ferro arm or laser tracker. My goal is to automate finding the minimum number of datum points and where they should be located along the beam. This problem is important because design engineers must provide a datum scheme in their released engineering that supports a verification team and their measurements. If you don't provide the right datum scheme and the beam is not supported enough, you could end up scrapping a part that is good or accepting a part that is out of tolerance. Solving this problem would be significant because it would streamline the way design engineers create a datum scheme for their parts. Automating this process will reduce the time it takes to determine these points and human error when performing these calculations. The basics of my code are that you enter the constants like length or modulus elasticity, and then I set up distributed weight and moment of inertia vectors. Then I send it through a for loop that increases the number of sections for each iteration, and each time it goes through this loop, the deflections will be taken on each of the sections, and the exit criteria for the loop is that it is either less than 3/1000ths of an inch deflection or until the maximum number of sections has been reached. Some pieces of my code required using an integration technique, and I've decided to use the left-hand Riemann sum method. With the way that data is being entered, a Riemann sum will have no error since the inputs are assumed to be uniform distributed weights, so basically they already look like stair-step functions. This code is designed for long beams, so a step size of 1 inch that I've done in my code is acceptable. The first beam deflection equation is for a simply supported left hand and right hand side with a distributed load. This is used in the case where you don't have any datums supporting in the middle of the beam, and this check has to be done just to make sure that your beam actually needs some datums in the middle. The second equation is fixed on one side and simply supported on the other. What this does is takes the end of our beam and then takes us to the first datum target. And then equation 3 is for fixed left hand and right hand, and this will be used for the intermediate sections with distributed loading. The assumptions I've had to make to use these beam equations are that fixed boundary conditions on intermediate sections better mimic canceling moments from the distributed weight from one section to another. So the sum of the moments around an intermediate datum labeled Fx are assumed to be 0 because the distributed weights kind of cancel out each other, and then the ends of our beam are going to be simply supported. The code I have written up to this point solves for the minimum number of datum target points, assuming the beam is split into equal lengths. This assumption is accurate for beams with uniform length and cross-section. However, the results from the code are overly conservative because one section of the beam could deflect 3/1000ths of an inch, and the other sections could deflect much less. This is why I will try to implement a genetic algorithm to solve for the optimal section lengths. In other words, equal deflection for all sections by the time the final report is due. If I am unsuccessful, this will be a good future project for another optimization student to improve the output of this code.